dimension is at least 2, at least 3, at least 4, but then you have to show that it's no more than whatever it is, right? And that's really tough. That's the hard part. So you can find an example of 3 points that can be shattered by, say, triangles, and then VC dimension is at least 3. And then you look for 4 points, and then it's at least 4, and so forth. At some point you can't find examples anymore, and now you have to find that they don't exist. You have to prove that they don't exist. Yeah, it was a similar argument. So let me tell you something about it. For several years I was using this particular homework, because it's really nice. You know, triangles, circles are kind of cool things to play with. And I always mellowed it down for the students. I said, you don't have to prove it. Just try to show, to give as higher bound as you can. In other words, find the highest set that you can shatter and tell me when you think you're there, but you don't have to prove it. And at some point somebody challenged me and said, okay, well, what is the real VC dimension? And I didn't know. So I went to Tom. I found it hard to prove, so I went to Tom Mitchell, who wrote the book and presumably knows the answer to these questions. And he said he doesn't know. So I went back to my office and I said, okay, this is embarrassing, I'd better prove it. And it was surprisingly difficult. I thought about it on and off for several days. I finally came with proofs for both. It'll take me a while to reproduce them now, but they're not trivial. The triangle was not so much of a problem. The circle was a real problem. So did you prove the circle too? Okay, good. That's excellent.
Actually, there's a trick proof for the circle.
Oh, I came up with the proof of the circle, but it was very tricky. I had a TA at the time who was also very mathematically inclined, so I think I bet him that I could do it, if I remember it correctly. It was already 3-4 years ago, but yeah. So there is an answer, and there is a proof, and I was able to derive it, but it wasn't easy. And my hats to anybody who proved it. Maybe you found an easier proof, which is even more impressive. Okay. So there's no need, I think, to go over more VC examples unless this is what you want to do in the review part.
Do you know what the actual answers are then?
Yeah, that's what I was saying. I do know the answer. I don't remember them right now, but yeah. So the natural answer is the correct answer. Namely, if you go trying to find larger and larger sets to shatter, at some point you get stuck, and it's not like there's a really clever way of doing it one more. So, but since you proved it, remind me of your name. I'm sorry, Matus. Since you proved it, you can tell us what the answer is. So what is it? The circles. 3? Yeah. Maybe you can shatter 3, but you cannot shatter 4, right? Yeah, I remember that. Yeah, so it has to do with, I remember it now, but we can do it together. So it's easy to do 3, and it's hard to do 4. And if you have 4 and they are a convex set, it's something about drawing this and then not being able to draw this, right? How long will it take you to show us?
A minute.
Please.
So you know that you have to have a quadrilateral, because if you have any points collinear, then you can't do it. So I can say without loss of generality that I have a quadrilateral. And then maybe I missed some of the cases, but the way...
Well, there is a case where one is in the middle of the convex hull of the other, so it's not a quadrilateral. It is quadrilateral, but it's not convex.
Okay, well I might have skipped some of the cases, but I did what I thought were the most difficult cases.
Okay, let me give you the other cases first. Let's make sure that we understand the collinear. If you have 3 points that are collinear, you cannot have a circle that includes the 2 on the outside and excludes the one in the middle. Okay? Then no 3 points are collinear. If no 3 points are collinear, either there's 1 point that's in the convex hull of the other 3. Stay close. I'm calling you back in a minute. Either there's 1 point that's in the convex hull of the other 3, or there isn't. If there is 1 point that's in the convex hull of the other 3, you cannot have the other 3 in and that 1 point out. Right? You cannot. If you have this kind of situation, you cannot include these 3 and exclude this one in a circle. So now we're left with a case where it is a convex polygon, convex quadrangle. Now we're yours.
I'm nervous because I haven't slept in 2 days.
Okay, well, if you can't do it, that's fine. Maybe it'll come back to me.
I ended up reducing it to the case, so I'm skipping all of this, but I reduced it to the case that you have to solve XOR. And so I was talking about rhombuses, so I have all these sides the same, and so it's going to look like all these circles and knots, other than knots and minuses. So the point is that if it's an exact square, then the circle is going to include all 4. If it's squeezed, then let's say without loss of generality that this is the shorter dimension. So I can say this is A and this is B, and the length of A is less than the length of B. Then I can make a circle which includes the shorter axis, but I can't include the longer axis, and I'll catch the other one. And if I make one that tries to dodge, then I have to include one of the other ones. And so that covers what was. I thought that was the hardest.
So my proof went very similar to that. You have a problem with alternating assignments, which is usually the case. And alternating assignments here, you draw the triangles, the diagonals, and you figure out which one is longer. There's a little complication in that one of them could be longer, smaller, but be near the edge. And then it turns out that you can. The idea is that you cannot. If you include this set, you cannot exclude this set. But it's not entirely true. Here's why I got stuck on it for several days. So I got as far as this. I'm now reconstructing from years ago. Let me draw it here. In general, you have 4 points. Call it the plus point, the minus point, the plus point, the minus point. And I want to show that there's at least one assignment of either these two being plus and these two being minus, the other way around, that cannot be done with a circle. And the way to show it is by drawing the crossing diagonals, and to argue that you can find a circle that covers these 2 points without these two, but not the other way around, or these two, but not these two. It doesn't have to do only with the length of the diagonals, because here's an example. Sorry, I'll put it here. Here's an example where this is the longer diagonal, but you can actually draw a circle that includes this point. Well, the idea is that this is so close to the edge that a curvature here will exclude it. So it doesn't have to do just with. It's not the case that you can always do the small one and not the large one. Sometimes it's the other way around. And I forget how I resolved this, but.
Well, when I was talking here, I had all 4 sides the same. I was saying that somehow when I did it, I reduced it to the case of having all 4 sides the same. In this case, I don't have this problem.
If they're all the same, then I agree with you that you cannot do that. But then the problem is when they're not the same. So anyway, it can be arbitrarily hard. But then this class is not about geometry or even combinatorics. It's just getting the idea right. So you can have fun with it, but it's not really machine learning. Okay, so what I still haven't talked to you about is some other sub-areas of computational learning theory, or some other penalty functions. So other way of, we talked about sample complexity. We talked about how many examples are needed in order to assure learning with some probability to some level of approximation, right? And you can think of a variety of lower bounds and upper bounds. We didn't discuss lower bounds, but you can think of setups where you can prove that you need at least these many examples to learn something that you cannot learn without it. One extreme case of that we did discuss is an unbiased learner. A learner that can represent any possible function. Remember I drew it on the board, which means any bit vector. If you represent every possible function as a bit vector of its values and all the inputs, they are 2 to the x possible functions, if x is the size of the input space. And I proved to you, not rigorously, but I proved to you that as you get more and more examples in your training set and you shrink your version space, your version space still contains a huge number of alternatives, and it will never go down to 1 unless you've seen all the examples. That's another way of saying there's no crosstalk between examples, between instances. There's no learning, there's no generalization, because there's no a priori restriction on the representation power of the hypothesis space. But even less extreme cases where there is a hard bias, you can sometimes prove, based on typically on counting arguments in terms of the size of the space that you start with, that you cannot converge fast enough. You cannot converge with fewer than so many examples. So this is about sample complexity. And then there's computational complexity, which we didn't talk much about. I don't think I defined for you what a PEC learnable is. So I should define for you what PEC learnable. I think I had it on one of the slides. Because PEC learnability has to do not only with the sample complexity, but also with the amount of computation that's needed to do the learning. So obviously, if you need an exponential number of examples, of training examples, then it will take you a computational amount of time, because presumably you need to look at every example at least once. But the other way is not true. You may be able to show that you can learn something with a less than exponential number of examples, let's say with a polynomial number of examples, and yet you may need to compute over them an exponential amount of time. But if you can do both, use a polynomial number of examples and finish the computation in a polynomial amount of time, that's called PEC learnable. So let me just flesh out the definition of PEC learnability. I may have had it before, I don't remember. So we talked about the two concepts of approximately learning something, and of learning it with, even that approximation, learning it with some probability, having some probability of failure or probability of success. So this is where the term PAC, or probably approximately correct, comes from. You have a class of possible target concepts defined over the instances X, some length N, and there's a learner, namely an algorithm, that uses a hypothesis space H. Notice we talked about the fact that H and C don't have to be the same, although often, for simplicity of analysis, we deal with cases where they are the same. And then we say that the class C is PEC learnable by the algorithm L using the hypothesis space H if, for any member of C that you choose as you as the teacher, choose as your target concept to be learned, and for any distribution curly D from which the data will come, over X, and for any degree of approximation epsilon, small number, the degree of tolerable error epsilon, and any delta, which is your tolerable probability of failure, for any such choice of epsilon and delta, and even choice of curly D, and a choice of a member of the target class C, the learner, the algorithm, will, with probability of at least 1 minus delta, output some hypothesis from H, such that its error under curly D is less than epsilon, and will do that in time that is polynomial in effectively the approximation level, the failure tolerance level, N, which is the size of the input, and the size of the concept size of the description of the target concept. So this is the formal definition of what we've talked about last time. It doesn't explicitly talk about sample complexity. It doesn't say use a polynomial number of examples, but since it runs only for a polynomial amount of time, it cannot touch or see more than a polynomial number of examples. One of the most powerful things here is that we don't care what the distribution curly D is. In fact, it could be a very weird distribution. It could be very peaked in some area. Right? It's funny. You're saying that you're going to learn a concept with high probability and with high accuracy, regardless of the distribution that is used to define the error. Right? This error is bound by epsilon for any given curly D. And the reason we're able to do that is because it's the same curly D that's used to draw the training examples. So we don't know what it is, but we know that whatever it was yesterday, it's going to be the same tomorrow. So this is what PEC learnable is about. Questions? Okay, so we talked about computational complexity, we talked about sample complexity, which are related but not the same. And now we can talk about the third kind of complexity, which is error complexity. Namely, how many mistakes, or mistake complexity, how many mistakes are you going to make along the way until you're done learning? This is often a very reasonable measure to use. So if you take on a new job, and you weren't trained for it, or maybe you weren't trained adequately for it, and they tell you, oh, that's okay, you learn on the job. Okay? Well, your boss probably doesn't care how many months it takes you to learn. They care more how many mistakes you're going to make along the way until you learn. So the setup is usually you have to start making decisions right away, even though you haven't really learned anything. The decisions could be classifications or decisions, actions on what to do, whatever. And somebody takes notes of how many mistakes you made. And after you've made your decision, in any one particular time, you're told what the correct answer is. So you can keep track yourself of the mistakes you made. And then you learn from it. So you learn not actually necessarily from the decision you made, but from somebody telling you after the fact what the correct answer is. So in the case of learning to play chess, it would be maybe your teacher standing over you, and you make the move. And after you made the move, the teacher tells you whether it was a good move or a bad move, or maybe shows you another move. And then you make another move, and then they tell you again. So they don't tell you in advance, they tell you after you made your decision. And you measure your progress and how many mistakes you made until you reach a certain level of performance. This is very, very useful in the case of portfolio management. If you're trying to build models of predicting stock market and predicting behavior of different stocks, and you're trying to balance your portfolio of stocks to achieve certain goals, you have to make decisions on what to buy and what to sell all the time, even before you are able to learn a model and make intelligent predictions. So what do? You make some decisions, and then a day later you see what happened. Or a week later, or a month later, you see what happened. Then you make more decisions. And you make decisions along the way, and you make mistakes along the way. And in fact, there's interesting work by Avram Bloom here at CMU. One of the earlier things he did in machine learning is called online learning algorithms. Online learning algorithms are exactly the kind of algorithms that do what we talked about now, namely, they have to start performing right away, and you learn online. You learn on the job. And the most commonly used way of measuring how well you do is sometimes how many mistakes you made, if it's a discrete kind of classification, but more often it is how well do you do relative to an algorithm that had the benefit of hindsight, an algorithm that was told in advance what the sequence of questions and answers would be, and was able to chew on it for a while and then make predictions on some other set. So presumably you take a hit for having to make the decisions online without, and being told things after you make the decision. How big of a hit are you taking? And one of the things that he was able to show is that some algorithms have the property that they are not too far off from the optimal algorithm, even though they're online. They're within a constant worse than the optimal possible. So this is the other notion of how do you measure learnability? By the number of mistakes you make. Let me give you an example from the slides. Okay. So let's say your hypothesis space is conjunctions of Boolean literals. So the input is n Boolean variables, and conjunction Boolean literals might be x1 and x2 bar and x5. We've dealt with this kind of hypothesis space several times before. So you're trying to learn something in this space, and you use an algorithm that should be familiar to you from a very first class called Find S. Namely, you start with the most specific possible hypothesis, and then you relax it in the face of data. So you start with x1 and not x1, which is kind of a weird thing to do, but let's do it anyway, and x2 and not x2, and xn and not xn. So you start with a hypothesis that includes all of the literals and all of the negations, which of course would say no to everything, because it contains a contradiction within itself. And now you look at all the positive examples. If you remember, Find S only concerns itself with positive examples, it ignores negative examples. Look at all the positive examples and you use them to modify this hypothesis to make it more general. And my question to you is, assuming that the target concept is an H, then it can be represented this way. I'm going to ask you not how many training examples do you need in order to guaranteed convergence to the truth, but rather how many mistakes are you going to make along the way. What's the largest number of mistakes you could possibly make using this algorithm? So just to make sure we understand the algorithm, you're given now a particular bit vector 1 0 0 1 1 0 0 0. This goes from 1 to n, and you're told that this is a positive training example. So you now have to knock out some components of this to make it consistent with this. For example, you know that x1 is 1, so this part cannot be true. The not x1, you rule this out. You know that x2 is 0, so this cannot be true. You rule this out. You know that x3 is 0, you rule this out. You know that xn is 0, rule this out. You go into the next training example. If it's negative, you ignore it. You skip over it. You go to the next one. Let's say it's positive. Again, you go over these and make sure that you cross out anything that causes your hypothesis to disagree with that positive example. So how many mistakes are you going to make along the way? Please?
N plus 1 mistakes.
N plus 1 mistakes. Why?
In the first case, you're going to remove n of the Boolean literals. And every other time that you present an example, if it's correct, then you'll remove at most one literal from the example.
If it's correct? If your prediction...
accepted.
Right. So if you're correct in if your current hypothesis is correct about this positive example, then you will not remove anything. You will not change anything. But if it is incorrect, if you made a mistake, then
you will remove one or more conjunctions from
right.
the litter.
Every time you made an incorrect prediction, it causes you to remove at least one literal from there. So after seeing the first example, we went from 2n literals to only n. And from then on, every time we make a mistake, we will take out at least one. And since there are at most n to take out, we will not make more than n mistakes plus maybe the first one, except n plus 1. So it may actually take a long time. I cannot put bounds in this particular setup on the time or the number of examples, but I can put a bound on the number of mistakes. So it's kind of a different way of thinking than thinking about how many examples you need or how much time you need. Let's take another example, more general one, also from the slides. Suppose you have a version space, and as you get new examples, it shrinks. But before it shrinks, you need to make predictions. It's an online algorithm. And the way you make a prediction is by taking a vote in the version space. It's a simple classification, yes or no. At any one point you get a new training example. Before you are told what the correct classification is, so it's used both as test and as training. First it's used as test, then it's used as training. First you are asked to make a prediction. So you do it by taking a vote in the version space. count all the hypotheses that are classified as positive, count all the hypotheses that are classified as negative, see which one is a majority, go with the majority, and after you made that prediction, you're told what the correct label is. Sometimes you'd be right, sometimes you'd be wrong. Now my question is, how many mistakes are you going to make until you converge?
I think it's n most log base 2 of n.
At most log base 2 of n. Of n? Or what is n?
And is the number of initial hypotheses.
The size of the hypothesis space. So let's call it log base 2 of h. Why?
Because you are using majority voting, so every time you are making a mistake, it means that at least half of the hypothesis agree that are making mistakes, and every time you rule out at least half of the left hypothesis.
Right. So every time you made a mistake, it means the majority of hypotheses in the inversion space made a mistake. Since we chose to go with the majority, if you made a mistake, so did the majority, and you crossed them out, which means you cut the size of your inversion space in that step by at least a factor of 2, because you threw out more than half. Now, if it turns out the majority was right, you will cut out the minority, which is less than half and maybe a very small minority, but it doesn't cost you anything in terms of mistakes. Again, the way we think about when we think about mistake bounds is very different. What matters is only the mistakes you make, not how long it takes you to get there. So if every time you make a mistake, the inversion space shrinks by at least a factor of 2, there can only be log base 2 of the size of the inversion space, or size of h, mistakes to make before you're down to 1. I want to show you one result without proof. It's kind of neat because it ties together mistake bounds and VC dimensions. So suppose you have an algorithm that is trying to learn concepts in a large class. So there's a concept class C, and you have an algorithm, we call it A here, learning algorithm A. And now you define the maximum number of mistakes that the algorithm can make on any member of the class. So it's a maximum over all members of the class. Of the maximum number of mistakes that the algorithm makes. So there are two maximizations here. One is over all members of the class. The second is over all possible training examples. Okay, there is a certain called arbitrariness or stochasticity to how many mistakes you're going to make. The same algorithm learning the same target concept may make a different number of mistakes depending on what training examples they're faced with. And if it's a stochastic algorithm, even with the same sequence of examples, might make different number of mistakes. But even a deterministic algorithm, faced with different sequence of training examples, would make a different number of mistakes. So take the maximum over that, the maximum possible number of mistakes that you could make with this algorithm before you learn, and then maximize that over all possible concepts in the class. This gives you a mistake bound on the algorithm itself with regard to that class. Now, try to optimize that over all possible algorithms. Namely, now try to find the algorithm that gives you an algorithm A that gives you the smallest value here. So let's say you are phobic about making mistakes. You want to minimize making mistakes at any cost under any scenario of making mistakes. Okay, so you're not even trying to minimize the average mistakes you make. You're trying to minimize the upper bound on the mistakes you make. You want some guarantees that you will not make more than this amount. This is the guarantee that you will not make more than this amount for any member of this class, for any training set. Now try to find an algorithm that minimizes this number. This is called an optimal mistake bound. And there's an interesting relationship between the optimal mistake bound and the VC dimension. So I gave you this, and you have an arbitrary non-empty concept class, and the optimal mistake bound for this class, written as opt of C, is the minimum over all possible learning algorithms A of M sub A of C. So since you're minimizing over the argument A, which is all the learning algorithms, you take it out of the equation and it becomes a property of the concept class itself. So we did maximization of mistakes over training examples, maximization of mistakes over all the possible concepts in the class, and then minimization of that number over all possible learning algorithms. So it's min, max, max. And when you do all of that, you're left with the property of the concept class itself. And I ask yourself, what is that number for this class? And the answer is this number can be bound both from above and from below. It's easy to see the bound from above. The bound from above is the log base 2 of the size of the concept class. And the reason is we can use the halving algorithm, the algorithm we just discussed now, of keeping track of the version space and taking majority vote. And that's guaranteed to cost us no more than log base 2 of C mistakes. So we can always do that. So that's an upper bound. The question is, can we do better than that? Are there classes for which there are bounds that are smaller than log base 2 of the space? And the interesting answer is yes, there might be, but there is a lower bound on the number of mistakes you make. And the lower bound is the VC dimension of that class. So once you calculate the VC dimension of the class, it gives you a guarantee that there does not exist an algorithm that is guaranteed that can be guaranteed to make fewer than these many mistakes. You have to talk in terms of guarantees of mistakes, because it's always possible that by fluke of how the training set was arranged, you will not make any mistakes. Right? It's always possible that you will not make mistakes if you're doing things, and you're lucky. But the more interesting thing to prove is that you're guaranteed not to make mistakes. And it turns out the VC dimension is a bound on how much guarantee you can provide. Okay, any questions about either this or any other part of computational learning theory? VC dimensions, sample complexity. Did I mention you the term active learning? Remember we talked about the setup where the student chooses the questions, the setup when the teacher chooses the questions, and the setup where a curly D function chooses the question. When it's the student, the learner, who chooses the question, this is known as active learning. And the reason that's important is because in the real world, many times, you are able to choose your learning examples. For example, in situations where it costs real money or real time or real effort to get more data, often you have discretion as to what data to get. Should I get this data? Should I get that data? Sometimes it costs money to get the data, sometimes it costs money to get the answers to the data. In the extreme case that I gave you, if you're a scientist, a biologist in a wet lab, and it may take you 2 person-years to get an answer to one simple question. So you'd better think carefully in advance which question you want to ask. So this whole subfield is called active learning. I think the other setup of the teacher choosing what to teach you next is somewhat less interesting, or well, I shouldn't say interesting, but somewhat less developed, perhaps because it doesn't correspond to a very commonly encountered situation. I mean, you can think of education as being such case, where the teacher knows what they want to teach you and they have to think of how to teach it to you, but real education of real people is of course much more complex than that. But in most situations of machine learning, there is nobody who knows the answer. If there was not somebody, and if they did know the answer, chances are they don't want to give it to you. So you're not in a situation where they're trying to give it to you and they're just trying to find a way to do that. Usually in a real-world machine learning problem, either you're free to choose questions, or the questions just, or the instances just come at you from nature. Okay, comments, questions? So let me tell you a little bit about the midterm. It's closed books, closed notes. However, I'd like you to have the ability to bring a short summary of formulas or anything else you want to summarize ahead of time, so you don't have to feel that you have to memorize things. So what I usually do, and what I'd like to do now, is to let you bring one sheet of paper, one 8.5 by 11 ordinary sheet of paper that you can write on both sides by hand, print, anything you want. You can even do it in font, I don't know, size 4-point font. I've seen people writing very, very small. Just summarize on it whatever you'd like to summarize on it. Let me explain to you a little bit why I do that. I don't like the idea of closed books, because I don't believe the world is closed books. I mean, when you are out in your job or in your research or whatever you do, there are books and you're free to consult them, and especially now with the web, it's very easy to consult other resources. So I don't want to test you on memorization. I want you to be to sort of integrate these concepts and understand them to the point where when you need to look up something, you go up and look it up, but you know exactly what you need to look up and you have the concepts in your mind. On the other hand, letting you have the books in class can lead to what we call just-in-time learning. So you may feel, oh, I don't really understand this material, but if there's a question about it, then I'll quickly go and look through it and figure it out. I want to avoid that, because I want you to do the learning during class time, not during the exam. So my compromise is, don't worry about memorizing long equations or numbers or anything like that. Anything that fits into a page is fine. And I found from my own experience as a student that summarizing a whole course into one page was just the right thing for me. It kind of gave me an idea of, I know what it's about, and when I came across it again a year or two later, I could in 2 minutes read that one page and basically remember 90% of what I need to remember. There's research that shows that people remember very little from classes, from lectures, from anything. So actually aiming for you to remember one page worth is a lot. It's very ambitious. So you don't even have to remember that a year from now. But if you remember enough, if you remember where you stored that page, that would be good. And then if you're able to cash it in by just reading one page, I think that's excellent. And I still go back to summaries that I have of books, of lectures, of courses, that I worked very hard on condensing them into one page, sometimes half a page, and it's great. I read it and it's like reading the whole thing all over again, almost. So anyway, so I'm doing it also because I think it's a great thing for you to do. So you can bring one sheet of paper, you can write on both sides of it. Please write your own sheet of paper. Don't make copies from other people. Okay? Seriously, because of this last issue, that the process of writing it is very important. Create your own sheet of paper, write your name on it, make a copy, and keep it behind, because I'd like you to turn in that sheet with your work. Okay, so make a copy and keep it behind. Also, please bring a simple log-enabled calculator. So you may need to do some log calculation. So make sure you can do that. What else? I think I mentioned it to some of you, maybe to all of you, that I'm not looking for, I will try to stay away from questions that require great inspiration. Because these, as you will find out in the second part of the class when we talk about, of the course, when we talk about statistics, these have great variance. You might get the idea within 5 minutes, or it might take you 2 days to get the idea, and it's not a good measure of. So I try to find things that have more to do with fundamental understanding. If you understand it, the answer is pretty obvious. It doesn't require much thinking or much inspiration. Try to stay away from many calculations, although I can't always succeed with that, but try to not make the calculation the difficult part of the problem. A question, please?
So there will be computational learning stuff on the midterm too?
Yeah, anything up until 5 minutes ago. Absolutely. Yes, please.
Will there be any review problems available, or will there be any review session that you will announce?
I wasn't planning on any. If there are specific things you'd like to review, we can do it right now. I've mentioned to some people who asked me that the problems in the book, many of them are, and that's the simple problems in the book, not the complicated things, not the things that require you to write code, and not the things that require you to carry on hairy proofs. But simple problems in the book would be quite typical, I think, of the kind of questions I would design. So I usually use this last lecture as a review lecture, and this year I have less than the full time. So what I would typically do is ask you if you have any questions, and if there are a lot of questions, we might kind of rank them by level of interest. So I was also asked about the relationship between lectures and the book and the slides, and what's on the exam and what's not. So the answer is, all the topics that I covered in class are in principle on the exam, and you should certainly know them. Now within each topic that I covered, there may be more material than I could talk about in class, and for that I'd like you to go to the book and read it. So if there are whole sections, certainly whole chapters in the book, but if there are whole sections in the book that I didn't mention, it will still be great for you to read, because it's a great book, but they're not officially part of the material. But if I talked about, for example, majority voting or mistake bounds, do go to the book and read that section and try to incorporate it into your understanding. Obviously, what I covered in class is what I thought was the most important, but sometimes there are things that I either don't get to, or I might even forget. Okay, so we talked about representation. And this led to discussion of hard bias. We talked about search, version spaces, and this leads to discussion of soft bias. I write it this way because you can classify things by the chapters, by decision trees, neural networks, but hopefully by now you get the idea that it's really not about the particular formalism. What I'm trying to teach you is not about what decision trees are like or neural networks are like, because tomorrow somebody will come up with not decision trees but decision stumps, which are real learning formalism. It's related to decision trees, and there are decision DAGs, and there are all sorts of variations on that. What's more important is to learn the tools of how to evaluate it. What is the representational power? What can it represent? What can it not represent? What is the hard bias? Given a specific learning algorithm, what is the soft bias? What is the preference bias? What is computational complexity of different algorithms? What is the difference between what decision trees do versus what neural networks do? What is the difference between these two biases? Somebody asked me that in class just the other day, if I remember, about decision trees. How would you characterize the bias of decision trees? Well, think about them. You're only allowed to ask about one attribute at a time, and the question is typically sort of a binary question, from here on, this way or that way, right? Even if it's not a binary variable. If you think of the input space for a decision tree, I'm going to draw it in 2 dimensions, but it's actually a much higher dimension. A decision tree, the question at the root corresponds to putting a line here and sending all the stuff that's in this direction to one child of the root and the stuff here to the other child of the root. Right, and then this one gets split maybe this way. And this one might get split here. Right, so this is the root question. And this is the question sitting on the right-hand side of the root, and this one sitting on the left-hand side of the root, and then makes this kind of division. So decision trees tend to split the input space into these cells that are made of lines that are parallel to the axis. Why are they parallel to the axis? Because they consult only one attribute at a time. If you allow yourself in the set of questions that you consider to consider combinations of attributes, now you start allowing yourself these diagonal lines too. It's just a way of visualizing how you cut up the space. But they have hard decision surfaces. Whether they're perpendicular to the axis or diagonal, they have hard decision surfaces. Neural networks, on the other hand, tend to be soft. Neural networks, if you start with very small weights, they calculate something that is more or less linear function, because the sum of the weights of the weighted sum of the inputs falls on the sigmoid at an area where the sigmoid is more or less linear. Once the weights start deviating from 0, then the weighted sum no longer falls in this linear range, no longer falls here, it starts falling here or here, and then the nonlinearity kicks in. And then you can see it in, if it's a classifier, you can see that the decision boundaries are curved and oddly shaped. If you remember the example of the vowels of speech. If it's not a classifier, but just a function that maps numbers to a number, then you get nonlinearities there as well. Information theory. I think information theory in general is very important, and I'm really sad that they don't teach it routinely as part of undergraduate education in computer science. I don't know if they even teach it as part of undergraduate education in math. I think it should be. Certainly should be part of statistics. But I've found way too often that undergrads just don't have it. So I think the concept, especially if you're going to deal with data a lot, either statistician, machine learning person, whatever, you have to understand these notions of where is the information, how you can quantify information, what does one piece of information tell you about another. So entropy, cross entropy, mutual information. The fact that mutual information is not exactly additive. It can be both sub-additive and super-additive in the following sense. If you have some function that you're trying to learn and you have several predictors of it, let's say x1, x2, x3 and so forth, are all trying to predict y, you can measure or estimate the mutual information between x1 and y and between x2 and y. But you can also measure the mutual information between x1 and x2 together and y, right? Because any two random variables can be thought of as one random variable. And I hope you remember that the mutual information between x1 and x2 and y is not necessarily the sum of the mutual information between x1 and y and x2 and y. So here we have mutual information between x1, x2 and y. And here we have mutual information between x1 and y plus mutual information between x2 and y. And what's the relationship? Somebody tell me what the relationship is? Which way does the inequality go? Please.
You want to say the left-hand side is greater than.
Left-hand side is this one is greater than. So you're saying like this. It could be the same, right? You're saying it could only be greater, it could not be smaller. Any other answers? So the answer is it could be all of the above. It could be equal, it could be greater than, it could be smaller than. I think the most common intuition agrees with your suggestion, which is when you add the contributions of two predictors, they don't necessarily add up. I mean, so after you have x1, adding x2 is not as useful as if you just brought x2 in the beginning. Okay? This corresponds to a common intuition about experts. You know, you have a rare disease, you went to consult, you have several experts to consult, you consult one expert. Once you consulted that expert, the benefit you get from consulting a second expert is reduced. It's not the sum of the benefit you get from one, the benefit you get separately from the other. This is definitely the most common case. However, there could be cases where the combination of the two experts gives you something that neither expert alone could give you. And we saw that thing in some of our homework, where one bit gives you no information about the outcome, x gives you no information about z, y gives you no information about z, but x and y together give you a lot of information about z. This would typically be the case. One common example is when z is determined by the XOR of x and y. Okay, that's a classic example. Some variations of that. But in the real world, most things are not XOR. So in the real world, I have to agree with you. This is this is what you meant? Yeah, this is by far the most common case, where the benefit you get from the two together is less than the sum of the benefits you get from each one alone. So it's good to develop an intuition with regard to these things. Actually, this case, even though I said it's counterintuitive and it's not as common, it's actually important to keep in mind, because you're trying to solve a machine learning problem. You're trying to determine which features to include in your system, which attributes to include in your system. And you cannot include everything under the sun because you don't have enough data to support that. So you're trying to choose the most informative features. And often it's quite feasible to calculate the mutual information between each one simple feature and the outcome you're trying to predict. So what we often do is we do exactly that. We scan a large number of possible features, a large number of possible attributes. Could be millions of them. And we calculate an estimated mutual information between each one of them and the output. And we use that as a rough heuristic to decide which features to include. But we have to remember it's a very rough heuristic. And there may be wonderful features out there that are not picked up by this method, because you need to take this feature in combination with this feature. The combination together as a single variable is what all of a sudden becomes useful. And to do that, you'll need to look at all possible pairs of features, which is infeasible. And if you find a way of doing that, then of course you only solved it a little bit. There's still a possibility of looking at triplets of features and so forth. So the general feature selection problem is intractable exactly for this reason. That you cannot really predict with certainty what the benefit is of any combination of features by looking at the benefit from each one of them alone. We still do it because that's the only thing we can do. But it's good to keep in mind that it is subject to this limitation. Okay, so we talked about this kinds of bias and search, and we talked about information theory. We talked a little bit about decision trees and neural networks. Gradient descent. Do we all know what gradient descent is? So we need to understand what the error function is. It's an error function over particular set of examples, either test data or training data. And with regard to each one, it's a function of what your current system produces versus what you want it to produce. If it's classification, it's a very simple error function, which is 1 or 0. You got it right or you didn't get it right. If it's mapping, numerical function mapping, then we typically use a quadratic error function, although we don't have to. So once we define the error as the sum over all the examples in your data, in some data set, of the errors, the target minus the actual output, let's say squared, what is this a function of now? Well, the error is a function of the parameters of your learning algorithm. If it's a neural network, it's a function of the weights. You could define it for decision trees. It'll be a function of the actual questions inside the decision tree, or maybe the topology of the decision tree. The other problem is we talked about decision trees as decision trees. They make classifications, so the error would be discrete errors, which is not as useful because you can't do gradient descent over it. But you could do that, and you could even define a smoother version of error and classification. Not to mention that decision trees, or rather trees, can be used not just as decision trees, but also as classification, as regression trees. They can be used to predict a number rather than a category. We didn't discuss it much, but you should keep in mind that it's possible. In fact, the more general and popular name for decision trees is CART, which stands for classification and regression trees. Regression is just a name statisticians give to predicting a numerical value of a function. It's a big misnomer. I don't know, how old were you when you learned what regression means? I was quite old. It was very confusing to me because you think of regression as all sorts of other things. There's a historical reason for it being called regression, but regression, all it is machine learning of a numerical function. So if you're trying to match a numerical value and you measure your success by the distance between what you predicted and what the number is, that's regression. If you're measuring it by did you get the right category or not, that's classification. There's a third kind of machine learning, as long as we're summarizing it, and that's called density estimation. That's when there is no input and output. There's just distribution of inputs. And what you're trying to do is to learn as well as possible the distribution of the input that you see. So if you take die, singular for dice, and you flip it, you toss it many times, and you record the outcome, and you try to estimate the probability of each one of the 6 faces. That would be a problem in density estimation. Strictly speaking, it's not a density because it's a discrete event space. In a more general case, it's a continuous event space. It would be called density estimation. If you're trying to estimate the distribution of heights in the population from a finite sample, you can think of that as density estimation. So machine learning and statistical estimation in general falls into one of these 3 categories. Classification, so just choose one of a finite number of categories, and either you're right or you're wrong. Of course, there are variations. You can choose k out of n categories or whatever. Classification, regression. So this is given an input, produce a category. Here this is given an input, produce a number. And you're measuring by how close you are to the correct number. And the third one is density estimation. And here you're not trying to learn a mapping. Here you're just given many inputs, and you're trying to produce a PDF, a probability density function, or in a discrete case, a probability distribution function. Where was I? How did we get here? What are we talking about? Oh, gradient descent. Thanks for reminding me. So we define an error, and let's say we're in the case of regression, which is what neural networks are most commonly used for, although they're also used for classification. Case of regression, our error is related to the numerical distance between where we want to be and where we are now. But where we are now is a function of the parameters of our system, and in the case of neural network, the parameters are the weights. So this is a function of the weights, and therefore this is a function of the weights. So now we abstract away all of this and we say we have an error surface which is a function from the high dimensional space of weights to a scalar value of the error, which is non-negative. And our problem is to find the one point in that weight space that corresponds to the lowest possible error. Sometimes we can solve that analytically, algebraically. Most likely, for the nonlinear cases, we cannot. So we resort to some iterative algorithms that try to find local minimum. And the most commonly used one, and the one I discussed in class, is gradient descent. To do gradient descent, you need the error function must be differentiable in what? In what arguments? In all of the arguments you're going to do gradient descent in. So in all of its weights. Sorry, that was a crazy question. So we need to figure out the error with regard to any particular weight. So sometimes it's a simple matter of using calculus and chain rule. Sometimes, as in the case of a multi-sigmoid unit network, it's a little more complicated. You need to do some heavy-duty use of chain rule and some intermediate results. This derivative depends not only on the structure of the network, but also on the transfer function. Right? We chose the sigmoid for a variety of reasons. It's nonlinear, which was important. It's continuous, which is also very important. It is a reasonable approximation of a step function. For some reason we like the step function, historically. But we chose it for another reason, and that is the derivative is particularly simple. Questions? Please.
Okay. A lot of the I'm just going to ask. A lot of the topics are also in the book that you covered, except for information theory.
Right.
So, what are some other resources we could use while studying information theory, besides, say, class or notes? So, there are many textbooks on information theory, and almost all of them cover exactly these topics in the first few chapters. So, they would typically have a chapter about information, a chapter about entropy, a chapter about mutual information, a chapter about cross-entropy. These are like the fundamental concepts of information theory, so they would typically be covered in the first few chapters. They would be covered in much more depth than I covered here, so they'll prove all sorts of properties of them. They will talk about the extension to the continuous case, where you have a continuous random variable. You can also define entropy and all these other properties. So you could go there. I don't know. I mean, it would give you a lot more information that you need for this course, although it's a great topic to learn. The one book that I used to sort of order my slides and use the terminology from is mentioned in the slides itself. It's a book by Abramson from the 60s. There's a much more modern book by Cover and Thomas, I think, just called Information Theory. I don't particularly recommend that you use it to prepare for this exam. I do recommend it as a general great book about
information theory. I don't know of any specific tutorials on information theory out on the web, but I'm sure they are there. Wikipedia. But I don't know that any of this is necessary. The slides and my lecture should have done. If you missed the lecture, yeah, do go to the books. Make sure you understand these concepts. Please.
Will the lectures be available on the web?
This is the first year we're taping them. I'm still not sure to what extent I should make them completely available. I should tell you that if you have a legitimate reason to miss any one particular lecture, then absolutely I should write to Rebecca and she will give you access to the relevant lecture. I'm reluctant to make it generally available for a variety of reasons. I'll share some of them with you. One is that I don't want people to stop coming to the lecture. Not because I need people to hear me. I mean, I can lecture to one person fine. But because I think it's tempting. I give you an example. There are lots of distinguished speakers' lectures at the School of Computer Science every year. And every year they're being taped. And every year when it's time to go, I say to myself, I'm really busy right now. I'll watch this later on tape. And I never do. So there's this counterintuitive or unexpected consequence that because something is being taped, you're less likely to watch it. So for that reason, I'm a little cautious now, and I'm not making it generally available. I want you to come to class. Not to mention that I want you to come to class even if I knew you would watch the tape. I want you to participate in class. I think this should be an interactive experience. But if you have to miss class, going out of town, you're sick, anything like that, write to Rebecca and she'll give you access to the necessary lecture. Please.
Will there be questions related to the application of the specific algorithm? So you give us a set of data and you say apply the ID3 algorithm to generate a tree.
Would there be questions like apply the ID3 algorithm to generating a tree? There could be, but not to the point where you're overwhelmed with calculations and have a large probability of making a mistake along the way. If I do that, I will try to make it something where it basically tests your understanding of the heart of the algorithm, as opposed to spending 20 minutes on just cranking through something that you fully understand and you're just cranking through it. That's the goal. You don't have to just ask things pertinent to the exam. You can also ask about other exciting things. Please.
Why is it called ID3?
I don't know. Do you know, Rebecca? It's not the most idiosyncratic name I've seen either. Well, it's probably called ID3 because they first came up with ID and then ID2 and ID3. It's just a guess. There's Q learning, and in machine learning we'll hit it towards the end of the course. Why Q? Actually, I think there is a reason why Q. I don't know. If you think naming in computer science is crazy, wait till you get to biology. Oh my gosh. You discover something you think belongs to something there, so you call it by some name, and then 20 years later you found out it has 20 other properties, and the properties you thought it had doesn't have anymore, but it still has that name. So it's I don't know. Well, I can blabber on. There's no problem. I mean, you've paid for it. Might as well blabber for 7 more minutes. I mean, you're free to leave too. I mean, I will not be insulted. But let's see what else I should tell you. But okay, we talked about representation. Did I miss a chapter? We have like chapter 2 is about here, and chapter 3 is here, and chapter 4 is here, and information theory is outside of chapters, and computational learning theory is chapter 7. Please don't take this as the defining curriculum. And if I forgot something, if it's in the slides, or if it's in the lectures, it's there. We talked a little bit about threshold functions, if you remember. We talked about what can you accomplish with linear functions. It's not in the book, but it's kind of a good thing to ponder. We talked about the fact that the number of possible linear thresholds grows with n, but not quite as fast as 2 to the 2 to the n. If you remember that, the number of different threshold functions on a cube, on a hypercube, grows like 2 to the n squared, roughly. So if you're given a large problem with a large n, and the points are drawn randomly, and they're labeled randomly with plus or minus, chances are it's not linearly separable. So random problems are not linearly separable. We talked about neural networks and the importance of the transfer function, whether it's continuous or not, whether it's linear or not. We talked about what happens when you have a recurrent neural network. We talked about regularization theory. Also, it's not in the book, but actually it is in the book in some ways, just not mentioned by name. So an example from the book and from the slides is when you, for whatever reason, you want to keep your weights small in a network. So you have a dual goal. Your goal is not just to reduce the standard error measure, namely to make your predictions as accurate as possible, but also you want to end up with a network that has either as few weights as possible or as small weights as possible for whatever reason. Then regularization means that you create a new error function that has both components in it, and you try to minimize that combined error function. So the new error function would be this plus some term called the regularizing or regularization term that would correspond to the weights. For example, it could be the sum of the squared weights with some kind of a constant here that allows you to do the apples to oranges conversion. That tells you how important is this goal versus that goal. Another example was from decision trees. At the very end of the discussion of decision tree, we said that sometimes your choice of which questions to ask at which nodes in the tree are influenced not just by a desire to create the most accurate predictor, but also you're cognizant of the fact that some questions are more expensive than others. They cost you more money. If you're a robot and you're trying to find your way out of the room, then going this way to see if there's a way out may be more expensive or less expensive than going this way to see if there's a way out. Or if you're a doctor and you're trying to make the diagnosis, maybe the most accurate way to diagnose something is with a very special blood test, but if it costs hundreds of dollars, you can do a series of other tests. It might take longer, it might be slightly less accurate, but it might cost less. So again, this is a case of regularization where your objective criterion, the thing you're trying to optimize, is not just accuracy. It's accuracy plus something else. And as you are supposed to see in your homework, in your decision tree homework, sometimes a tiny difference, a tiny change in the heart of a recursive algorithm can lead to completely different results. And your homework was about pruning, when you apply the pruning. But if you imagine ID3 in general, if it has this information gain, or what we call mutual information criterion in there, if you change that criterion by a little bit, it can lead to vastly different trees. Question?
This is about gradient descent. So you have the error function. You basically have the whole function, right? It's available to you, and then you do gradient descent on it. Why can't you just? And then there's the issue of are we going to reach a global minimum or a local minimum? Why can't we just compute the global minimum, because we have all the information that we need?
So you're saying you hold in your hand the function. Why can't you just find its global minimum?
Yeah, why do we have to do the whole descent?
Right. And the answer is, if the function is analytical, which I guess it is here. I mean, you can write it down as a sequence of additions and subtractions and multiplications, right? It's a summation over something where this is a constant. This, in turn, is a complicated summation and taking the sigmoid of different things. What you end up with is a behemoth of a function, but it's a function. It has the property that if you plug in numbers, it's very easy to calculate what comes out. But you can then take the derivative of this entire function. But since it has many local minima, so to answer your question in the most general way, a high-dimensional function, finding the zero or the minimum or the maximum is not easy. I mean, there's the whole branches of math devoted to doing that. Finding zeros of a function, or finding minimum or maximum of a function. And gradient descent is one of the standard ways of doing that. There are other methods like Newton-Raphson, okay, where you start from some point and then based on the slope there you shoot by a large amount. It's also an inductive procedure, but it's not gradient descent. It doesn't take tiny steps. It takes larger steps. It has some other properties. It'll converge faster, but it does have a bigger chance of not converging. Okay, I'll let you go.